We're going to determine molecular shapes using VSEPR. The first step is always going to be to determine the Lewis dot structure of the compound. Once you have determined the Lewis dot structure, you want to count the total number of charge clouds around the central atom. A charge cloud can be either a bond, whether it's single, double, or triple bond, still counts as one charge cloud, a lone pair, or even a single electron. Then you're going to arrange these charge clouds in a way that minimizes repulsion between electron-rich areas. Repulsions are minimized when each electron group is as far away from each other as possible. To discuss the arrangement of charge clouds, we're going to introduce a concept called a steric number. A steric number is the total number of electron clouds around the central atom. So it's going to be the bonding groups of electrons plus the non-bonding groups. We want to minimize repulsion between the electron groups that are on the center atom, and we do that by placing them as far apart as possible. If we have a steric number of 2, that means there's 2 groups of electrons around the center atom. This red ball in each case represents the center atom. These extensions here represent either a bond to an atom or simply a charge cloud, whether it's a pair of non-bonding electrons or a single electron. For a steric number of 2, these clouds can be as far apart as possible simply by placing them at 180 degrees relative to each other. For a steric number of 3, the angle is 120 degrees. A tetrahedral shape applies for a steric number of 4. This is a 3-dimensional geometry. It's no longer all in the same plane as it is in trigonal planar, but it's a tetrahedral geometry. This AXE notation is incredibly useful. A represents the center atom, which is represented in each of these pictures as the red ball. X refers to an outside atom. More specifically, we have a bond to an outside atom. E represents a lone pair. So if we look at this representation AX2, it means we have a center atom that has 2 bonding atoms on either side. The molecular geometry, if you had an AX2 type molecule, is a linear geometry. Okay, note our steric number is 2. These bonds are as far apart from each other as possible. For a steric number of 3, there are 2 possibilities. We can have each of these charge clouds being bonding clouds, i.e. bonds to atoms. In AX2E, we have 2 bonding regions and 1 non-bonding region. Okay, let's look at some examples of each. Carbon dioxide is a linear molecule. If we look at the center atom of carbon, we see that there are 2 charge clouds. Remember, double bonds count the same as single bonds. So there's just 2 charge clouds around the center atom, and the molecule is oriented in a linear geometry. SO3 is of the type AX3. We have a center atom, sulfur, and 3 outside atoms. Each of the charge clouds around the sulfur is a bonding type of charge cloud. That's why it's AX3, steric number of 3. SO2 is AX2E. That means that there's 2 bonding regions and 1 non-bonding region, this lone pair. The lone pair takes up space. It actually takes up more space in a molecule than bonding areas do. So SO2 is based on a steric number of 3. The charge clouds are in a trigonal planar geometry, 120 degrees angles. However, when we look at the molecular geometry, we look only at the relative position of these nuclei. So the molecular geometry of SO2 is a bent geometry. It's a bent molecule. The molecular geometry of SO3 is trigonal planar. And the molecular geometry of CO2 is linear. Okay. Taking a few minutes and being able to translate the meaning of this notation is going to be very helpful in determining the molecular geometry of these different molecules. There is 3 possibilities for a steric number of 4. Again, we're using a notation where A represents the center atom, X is an outside atom, and E represents a lone pair. AX4 means that each of these charge regions is a bonding region, and each of these dots is going to represent an atom that is bonded to this center atom. AX3E, we have 3 bonding regions and 1 non-bonding region. So we see 3 bonding regions and 1 non-bonding region, which is here represented by a lone pair, a pair of non-bonding electrons. AX2E2 has 2 bonding regions, one's behind here, one's here, and we have 2 lone pairs, or 2 non-bonding regions. Each of these regions counts as a charge cloud. All of these have a steric number of 4, so all of the geometries here are going to be based on a tetrahedral geometry. So anytime you have a steric number of 4, the overall geometry is going to be based on a tetrahedral. The difference between these 3 is whether or not there are lone pairs, and if there are lone pairs, whether there's 1 lone pair or whether there's 2. Some examples. Methane is an example of an AX4 molecule. There's 4 regions of charge around the center atom, each ending in a atom. NH3, ammonia, is an example of a trigonal pyramidal geometry. There's 3 bonding regions, 1 non-bonding region. When we identify the molecular geometry, we look solely at the position, relative position of these atoms to each other. This is a trigonal pyramidal geometry versus the trigonal planar geometry that we saw on the prior page when we had no lone pair. Water is a classic example of AX2E. The overall electron group geometry is based on a tetrahedron. 2 of the positions are taken up with lone pairs, so the resulting molecule, the relative position of those nuclei, is a bent geometry. You are going to be asked to determine the molecular geometry of a molecule. It's going to be one of these 6 types. If you have a steric number of 2, it's going to be a linear molecule. A steric number of 3 can be one of 2 geometries, depending upon whether or not there's a lone pair. If there's a lone pair, it's bent, otherwise it's trigonal planar. A steric number of 4 has 4 possibilities. It can either be tetrahedral if there's 0 lone pairs. If there's 1 lone pair, it'll be trigonal pyramidal. If there are 2 lone pairs, the geometry is going to be bent. So the overall procedure is to first determine the Lewis structure and then classify the molecule type. We're going to write the Lewis dot structure of SO2. First, we determine the number of valence electrons. We see that there's 18. That means there's 9 electron pairs. Here's our skeletal structure. We want to connect up the outside atoms. That uses 2 of our 9 electron pairs. And we complete the octet of the outside atoms. Now that's 8 out of our 9. We have 1 electron pair left to put on the sulfur. We see sulfur is electron deficient, so we need to have 1 double bond. So we're going to use one of these lone pairs on one of the oxygens to form a double bond. Doesn't matter which side, they're both equivalent. and we're going to rewrite our compound. So here's the resulting Lewis dot structure. We see that the steric number is 3. There's 3 regions of electron density around the center sulfur, and 2 of the regions are bonding regions, 1 non-bonding region. That means our overall molecular geometry will be bent. This compound is formaldehyde. We see that we have 12 electrons. That means 6 electron pairs. We can connect up our center atoms to our outside atoms. Now we want to complete the octet of the outside atoms. We see that both hydrogens have a complete octet. Remember, they only need 2 electrons for an octet. Oxygen needs an octet. We've only used 3 of our 6 electron pairs. We can use our remaining 3 electron pairs to complete the octet on oxygen. Now we are out of electrons. We have no more electrons to give out, but carbon is electron deficient. So we're going to use one of these lone pairs to make a double bond. Here's our resulting Lewis dot structure. We see carbon has 8 valence electrons, 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Each of the hydrogens has 2. This is a valid Lewis dot structure. We look at the center atom. We see that there are 3 regions of electron density around our center atom. So our steric number is 3. Each of the regions is a bonding region. So this is an AX3 molecule, resulting in a trigonal planar geometry. This is a perchlorate ion, ClO4-. We count up our total number of valence electrons. We see we have 32 valence electrons, 16 electron pairs. First step is to connect up all the outside atoms. Then we complete the octet of all those outside atoms, and we will see that we've used all of our valence electrons, which is fine because chlorine has a complete octet as well. So to finish off the Lewis dot structure, we can just indicate the whole thing has a net -1 charge. We see our steric number is 4 because we have 4 regions of electron density around our center atom. They're all bonding, so this is the type AX4. There are no lone pairs. Therefore, our molecular geometry is going to be tetrahedral. This is the ammonium ion. We count up our valence electrons, and here we note that we have a positive charge, a net positive charge on this ion. That means we've lost an electron. So we have to subtract 1 electron from our total, and that yields 8 valence electrons, 4 electron pairs. We connect up our outside atoms on the skeletal structure, and we see we've used all 4 of our electron pairs, but that's fine because all of our atoms are happy. All of our atoms have a complete octet. We see our steric number is 4 because there's 4 regions of electron density around the center atom. Each of these regions is a bonding region, so it's of molecule type AX4, corresponding to a tetrahedral molecular geometry.